So this question here is talking about C6H12O2. So that's the formula. And then I got spectrum here. That's a polar 13 based on the number of the signal scale is 0 to 200, right? That cannot be the proton anymore. So that's a polar 13 anymore. IR shows a peak, even though spectrum is not shown, but it recognizes we have a peak 1740, right? 1740, that is where the typical carbonyl shows up, but it's a little higher than normal carbonyl, right? So that indicates what we have. Aster, right? We have an aster. And then the NMR, the proton NMR, is like a singlet at 3.6 ppm, another singlet at 1.2 ppm. That's a little puzzling, so we're going to talk about that. First of all, the degree of unsaturation, we talked about it. It's the number of the carbon, subtract the half of the hydrogen, you add half of the nitrogen, plus 1 is the formula. You do that, and you're going to find out degree of unsaturation in this molecule is just 1. And then that 1 just is a carbonyl of the aster. So we already figured out how that could be. And so let's figure out what else. We have the peaks and carbon 13 peak and over 18 and 180. That's the one that aster, right, showing right here. Nothing here, so that means that we don't have a no aromatic molecule, we don't have a no double bonds. Right? That's what it basically points out. We got other peaks showing up is pretty upfield. Some little bit getting to the 60, but not even, I mean, not all the way down there. But anyway, we don't have we got aromatic carbon. And so this is the only thing we can pick it up. We got aster based on that, and we confirmed by this is definitely. But the thing is that what is really intriguing is a proton NMR. The singlet and singlet, we only got 2 peaks for proton NMR, even though we have a 12 hydrogen. So there's so many number of the hydrogen, but you're only going to see just 2 peaks, and each one's going to be singlet. That is very, very intriguing. And this is something that maybe you need a little, I mean, you need to see this question to know what it is, probably. I mean, it's going to be really difficult to guess without knowing how to solve this question in prior opinion. I mean, what normally things shows a singlet in the proton NMR? For instance, methyl groups, right? Methyl, I mean, isolated methyls, having no hydrogen in the middle. That could be a singlet. So it could be either of this, it could be that. But the thing is, 12 hydrogen, if you got the methyl groups there will be the 4 methyl groups, right? 4 methyl groups. If each methyl is showing up, then you should have a 4 peak, but only have a 2 peaks. So there must be some symmetry in the molecule. If you have like an isopropyl, this methyl is the same as that methyl, but they are not going to be singlet, right? Because of these hydrogens will split this doublet for each, So 2 methyl groups in isopropyl is not going to give the singlet, even though those 2 methyl in isopropyl is the same. But if you keep adding it up, what about keep butyl? This methyl is equivalent to that methyl groups. That is equivalent to this one. So it's all 9 hydrogen is going to be singlet. So that is where you should think about. Whatever it is, and then if you got the 1 methyl groups, 2, 3, 4 methyl groups there, but they're not having 4 methyl groups separated out. It looks like a 1 methyl groups and then 1 methyl groups. And then there will be 12 hydrogen there. And then that's the reason you get just 2 peaks. So we know, I mean, this is 1, 2, 3, 4, 5, 6 carbon. So we found all the carbon, we found all the oxygen, we found all the hydrogens. Now we need to put them together. So the question is going to be put them together this way, or is going to put them together the other way? The thing is, this methyl goes to the carbonyl, this methyl goes to the oxygen. Which way should it go? How can you figure it out? What information do you think you need? If the methyl groups connected to the carbonyl layer, where the chemical shift of the methyl group may show up? Next to the carbonyl, that should show like a 2.1, right? We don't have a picture in 2.1. We got picture in 3.6. So peaks at 3.6 means this carbon should go to the oxygen. That way, it could be issue. If that methyl is next to the carbonyl groups there, that's going to be showing a 2.1. So this NMR signal is going to be invalid. So that piece of information is telling us this has to go to an oxygen here. So then this will be that. So that's how you're going to figure out where you're going to put it together, how you're going to put them together. Okay. All right, moving on. This will be probably more challenging compared to the other one because you can see that I don't even have a formula there. I got nothing. I got 3 spectra. That is a proton NMR, that is a carbon 13 NMR, that is a mass. No IR given. Still, we can solve. I mean, most likely NMR will do the most of the work for finding the structures. But because we don't have a what is a mass formula of the molecules, at least we can think about using molecular ion pig to get an idea of how big the molecule is. So we have 2 pigs showing 170, 172. Most of the time, the pigs having a highest number, that should be the molecular ion pig. So do you think this molecule, whatever the molecule is, having the molecular weight of 172? I mean, that would be the most of the time we're guessing it. But in this case, what you need to pay attention is, the peaks at 172 is equal times 170. There's only one particular element can have an equal abundance of the +2 mass, which is a bromine. So having this double peak showing here, 170, 172, meaning that the molecular ions are 170, and the 172 is isotopic peak, happen to be just equal time. So that means that we have a bromine there. Anyway, the molecular weight is 170. So the 170 and the heavy bromine there. And then from that, what else we can point out is that you got 91, right? So 170 and 170, you subtract the 91, then what you get, that's why you probably need to bring the calculator. You get 79. What is a 79? It's a bromine. So when the bromine takes off, it becomes a fragment. And then because there's no bromine, we shouldn't get N+2 isotopic peak. It's not there. So this peak doesn't have a bromine, already showing it. And then mass by itself, 91, is basically, the difference is 79, tells us that whatever this peak fragment is, the bromine is taken off, and then make the other molecules called cat. Another thing is, we got doublet, 7 and 8 ppm regions. So that is aromatic regions. So most likely we have benzene. And then by the pattern, this should be the para-substituted benzene, para-disubstituted benzene. So we got C6H4 as a piece there, it's a para-disubstituted there. And then to confirm that, we got the carbon 13 are having 4 peaks in these regions. So that the 6 carbons of the benzene is giving out the 4 carbon peaks because there's a symmetric molecules. All right, so we figure this one out. And then there's this 3 hydrogen that can be the methyl groups, right? But anyway, just trying to make sure that This is what we just talked about. Whatever thing is 91, I don't know what the whole thing is, but at least we figured out this fragment, and this is C6H4. The mass is a 76. If you subtract it out from this number, then you go to C15. That 15 is corresponding to the methyl groups over there. So that means now we found all the pieces. So we got all the pieces for the molecule from the molecular weight. We found out the presence of bromine by the isotopic field and close to isotopic field. And then we found the presence of disubstituted, para-substituted benzene from this signal. And then we basically, when we found the pieces, we keep subtracting these out and we try to figure out what else we need to find out. And then basically there's just one methyl group left over. And that methyl group should be this one. The chemical shift is between 2 and 2.5. So that is typically next to the benzene or next to the carbonyl. But in our case, we don't have carbonyl, so it's trivial. The methyls are directly connected to aromatic with benzene. So methyl groups go connect to this one. Bromine connect to the other one. So that should be the molecule in giving out the spectra.